carbon dioxide cold traps on the moon. Carbon would be very valuable to have on the moon, so that is a part of the motivation for this study. Now, I think we all know what cold traps are. At low temperature, the sublimation rate just becomes negligible, so these areas should accumulate ices. And there are various sources how volatiles are delivered to these cold traps over time. For example, comets. So comets include various ices, including CO2 ice, whereas H2O kind of several potential sources. And we don't really know what these delivery rates are, but we have plausible estimates. So, for example, for H2O, 100 kilograms per square meter per gigayear, that'd be 10 centimeter per gigayear, is easily plausible, and that would be the sublimation rate at 109 Kelvin. Now, there are other loss processes as well, but sublimation is a hugely important one, so it's a determining factor for accumulation of a volatile. Now, for CO2, plausible delivery rates might also be 100 or 10 kilograms per square meter per gigayear, and the density of solid CO2 is 1.7 grams per cubic centimeter. So, 10 kilograms per square meter per gigayear, that's 6 millimeter of CO2 ice in a billion years, and that is a sublimation rate at 56 Kelvin. So 2 Kelvin temperature difference is an order of magnitude difference in the sublimation rate of CO2. Now, over what time do they accumulate? Well, it's either the age of the crater, or it's the time since that area is permanently shadowed, and that's at most 2 billion years or so, when the moon was tidally locked into its current spin axis state. The PSRs are definitely not much older than that. And to map cold traps, one can of course use a diviner temperature measurement, surface temperature measurements. There is 11 years of these measurements we have used, and divide them into first local time, or not local time directly, but rather subsolar longitude, but also its season, right? So there's this draconic year, which is somewhat shorter than the Earth year, and over this draconic year, the solar declination changes by a few degree. And this map here, it's an interesting map. That's the ratio of the amplitude of diurnal temperature variations to the amplitude of seasonal temperature variations. So in most places, the diurnal variation, the lunation, is bigger, but at the floor of some of these PSRs, actually, Haworth and Shoemaker, actually the seasonal variations are bigger. So it would be a mistake to neglect the seasonal variations if one is interested in PSRs, temperatures. And then one can just calculate the time-averaged sublimation rate, and it is customary, and has been customary, that instead of taking a time-averaged sublimation rate, one just takes the sublimation rate at a peak temperature, because the sublimation rate is so sensitive to temperature. However, that is an approximation, and it's better to take the time-averaged sublimation rate, and in particular for a CO2, that turns out to make a huge difference. So for H2O cold traps, it already made somewhat of a difference. For CO2 cold traps, makes a huge difference. And so this is a map of water ice cold traps we published last year in the Planetary Science Journal. And the using max T instead of mean T just gives fewer cold traps and a smaller cold trap area for H2O, and the change from max T to mean T makes more of a difference than a choice in threshold. So if a threshold was not 100 kilograms per square meter by gigayear, but 10 or 1,000, it makes less of a difference when it's changing methodology. So the methodology is important in this sense, even for water ice cold traps. Oh, I should add what was I showed here was the South Polar region, pole of 80 south. So now here, so this is data for one spatial pixel divided into 24 times 6, so it's 144 time bins. And so the seasonal bin is the ecliptic longitude here on a vertical, and the fifth bin is summer solstice, and the horizontal is subsolar longitude, which is linearly is just shifted from local time by a fixed constant. And so we see here the peak temperatures occur sometime in summer. Now there are bins which are not filled. So although we have 11 years of data, but the spatial bins are very small, and there is millions of spatial bins in the polar regions that I showed. And each of those is divided into 144 bins. And so what we do, we fill these empty bins with the average, block average, sort of nearby filled bins. And then we can just form the mean value. And so, here, if I average these bins, we'll get the mean temperature, but you can also calculate a sublimation rate for each of these bins, and then average these sublimation rate to get a proper time averaged sublimation rate for CO2 or whatever volatile one seeks to study. Now, what is the sublimation rate of CO2? Now, it's so small it can't really be measured in a laboratory, so one has to extrapolate it to lower temperatures. And one can either measure the saturation vapor pressure, or one can measure the sublimation rate. And they're closely related by what's called the Hertz-Knudsen formula. And really this Hertz-Knudsen formula is, ideal gas, the flux of ideal gas molecules through a planar area. And if the pressure is the saturation vapor pressure, then that equals the flux from a solid out, for example, solid into vacuum. And so just this simple physics provides this expression. And then there's a prefactor alpha, and that prefactor one can have sophisticated discussions about. Recently, Persad and Ward wrote a 40-page review about this prefactor, and I assume it to be 1. I mean, it's been between 0 and 1 or something very close to 1. I make the conservative assumption that it's 1, and at low temperature it should be close to 1. And then one just needs some measurements from various sources and a robust expression to extrapolate, say, the vapor pressure to lower temperature. And here there is a theoretical formula for the lower pressure, for the saturation vapor pressure. So if temperature goes to 0, the log of P goes to minus infinity, and therefore P goes to 0 as it should. But not every function which is fit to these vapor pressure data has this robust behavior. So this diagram shows 4 different parameterizations. Now the relevant temperatures are like 50 to 60 Kelvin when most of the sublimation happens in something which is potentially a cold trap. And so at that area, 3 of the 4 agree. The only one which does not agree is the International Critical Tables, but that's a century-old, that reference. So and these are extrapolated values, right? So that's okay. And from the other 3, 2 do not robustly extrapolate to low temperature. So I picked Bryson et al. 1974, which just has 2 constants, A minus B over T. Now another potential issue in asserting what's the sublimation rate really at low temperature is whether there's a phase change. So for example, H2O ice changes from crystalline to amorphous at low temperature. Now for CO2, solid CO2, it's crystalline to at least 50 Kelvin, maybe even 30 Kelvin, so at the relevant temperatures. That's not an issue. And now here is, again, the 24 times 6 spins. But now temperatures are converted into sublimation rate. And this is a log of the sublimation rate. And even though it's a log, you see that 2 pixels dominate the sublimation. So most of the sublimation rate happens in summer at a particular local time. And so if one just picked the peak value, right, one would end up with something almost 1,000 kilograms per square meter per gigayear. But if one does actually the time average, because most of the time sublimation is really negligible, we just get 12 kilograms per square meter per gigayear. Now, 12 kilograms per square meter per gigayear, that's a very plausible, very realistic sublimation rate. And this pixel here is the LCROSS impact site. Not during impact, but from data before and after impact. And so the CO2, the LCROSS impact site is a CO2 cold trap. Right? These data tell us. Now here's now a map of CO2 cold traps, a preliminary map. We're still fine-tuning the data processing pipeline. And what's shown here is, areas with sublimation rates of 0 to 100 kilograms per square meter per gigayear. And there is some coherent, right? There are coherent patches of CO2 cold traps, at Haworth, in this unnamed area between Haworth and Shoemaker and an Amundsen. At Capeos too, but just, it's a tiny cold trap. But even if one picked 10 kilograms per square meter per gigayear, we would still have patches there. So we're talking about 300 square kilometer, roughly, of CO2 cold traps, concentrated mostly in a few areas. If you had just picked the peak temperature, the area would be much smaller and would be less coherent. And so, the coherent areas make it, the spatial coherence of these patches make the data analysis more compelling. One can also look at subsurface stability. So suppose that CO2 ice is covered by a sublimation lag. Well, it turns out, through temperature modeling, subsurface temperature modeling, that at a few centimeters of sublimation lag increases this area, by a factor of by an order of magnitude easily. So a sublimation lag will allow CO2 ice to be around the much larger areas from or any other form of burial would do that too. Now this is a somewhat enlarged map of Capeos, and a white circle here is the LCROSS impact, which has very low CO2 sublimation rates there. But of course, and I argue, right, if CO2 was observed by LCROSS, so that sort of confirms it's consistent with this prediction of these maps. But of course, then all the other species LCROSS detected should be cold trapped too, right? And so there's hydrogen sulfide and ammonia and sulfur dioxide and ethylene and CO2. And the next slide here shows sublimation rates for all of us. So SO2 and NH3 are less volatile than CO2, right? So they're between H2O and CO2. So they are cold trapped too, follows automatically. So at least these 4 species are cold trapped. Now, hydrogen sulfide actually has several phases at low temperature, and the only one we know the sublimation rates for is phase 1. But at the temperatures which prevail today, it will actually form in phase 3. So it's inconclusive whether hydrogen sulfide phase 3 is actually more or less volatile than CO2. And the only species I cannot explain is ethylene. I cannot explain for cold trapping is ethylene. But H2O, SO2, NH3, and CO2, which are species detected by LCROSS, are explained by cold trapping. Now, carbon, of course, can be very useful. We need it for steel. We need it for biological materials. And but there are these cold traps, CO2 cold traps, occur only in small areas, concentrated areas. So they are definitely special regions. Conclusions, which are listed here, but I am out of time. So there is evidence, coherent evidence for CO2 cold traps on the moon.